High in Lebanon's Bekaa Valley, 70 kilometers from the Mediterranean Sea, stand the ruins of a temple that defies comprehension. The Romans called this place Heliopolis, the city of the Sunday. But long before Rome's legions marched into these mountains, something extraordinary happened here. Something that would challenge engineers for 2 millennia to come. In the foundation of the Temple of Jupiter lie 3 stones. Each weighs approximately 800 tons. To put that in perspective, that's more than 4 fully loaded Boeing 747 aircraft. More than 8 times the weight of the Statue of Liberty. These aren't rough boulders rolled into place. They're precisely cut rectangular blocks, fitted so tightly that you cannot slide a piece of paper between them. And here's what makes this truly remarkable. These stones were quarried 900 meters away, transported across uneven terrain, raised 7 meters into the air, and positioned with millimeter precision. Without cranes, without internal combustion engines, without hydraulic jacks or steel cables. The Romans, or whoever placed these stones, accomplished what we would struggle to replicate today. This is the story of Baalbek, a place where human ambition met the laws of physics and somehow won, where ancient engineering pushed the boundaries of what should have been possible. This isn't a story about aliens or lost Atlantean technology. It's something far more impressive, a testament to human ingenuity, determination, and an understanding of mechanics that we're only now beginning to fully appreciate. If you're intrigued by mysteries that have real answers, hit that like button. Drop a comment telling me where you're watching from and what other ancient engineering marvels you'd like to explore. And whether you're watching or just listening, the story I'm about to tell will change how you think about what humans can achieve when they set their minds to impossible tasks. Let's journey to Lebanon and discover the truth behind the stones that shouldn't exist. Baalbek sits at an elevation of 1,170 meters above sea level in the Bekaa Valley, a fertile plain between the Lebanon and anti-Lebanon mountain ranges. The site has been sacred for millennia. Archaeological evidence suggests continuous human occupation dating back to at least 9,000 BCE, making it one of the oldest continuously inhabited places in the Near East. The Phoenicians were the first known civilization to build extensively here, constructing temples to Baal, their sky god, sometime before 1000 BCE. When Alexander the Great conquered the region in 332 BCE, he renamed it Heliopolis. But it was under Roman rule, beginning around 15 BCE, that Baalbek witnessed its most ambitious construction project. The Roman Emperor Augustus ordered the construction of a temple complex on an unprecedented scale. The Temple of Jupiter would become one of the largest religious structures in the entire Roman Empire. Its remaining 6 columns each, 22 meters tall, give only a hint of its original grandeur. When complete, the temple featured 54 massive Corinthian columns supporting a roof that could be seen for miles across the valley. But the true engineering marvel lies beneath your feet. The podium upon which the temple rests is a stone platform measuring roughly 48 meters by 88 meters. To create this foundation, builders used stones of increasing size. Most weigh between 50 and 100 tons, already impressive by any standard. The granite columns visible today each weigh about 60 tons and were transported from Egypt, floated up the Nile, across the Mediterranean, and then hauled 40 kilometers inland from the Lebanese coast. Then there's the Trilithon. 3 stones. 3 massive, precisely cut limestone blocks forming part of the western wall of the podium. Each measures approximately 19 meters long, 4 meters high, and 3.6 meters deep. Geologists and engineers have calculated their weight at roughly 800 tons each. Some estimates go as high as 900 tons. They sit 7 meters above ground level, resting on a foundation of smaller, though still massive stones. What makes the Trilithon unique isn't just size, it's precision. These blocks are cut with smooth, flat surfaces. They're positioned with minimal gaps between them. The joints are so tight that early archaeologists couldn't determine where one block ended and another began until they examined the stones from different angles. This isn't rough stonework. This is precision engineering. When you stand before the Trilithon, the human mind struggles to process the scale. A single one of these stones contains more than 240 cubic meters of limestone. If you tried to recreate this structure today using conventional stone blocks, say blocks weighing 1 ton each, you'd need 800 individual pieces to equal the mass of just one Trilithon stone. The sheer audacity of using blocks this size is breathtaking. And then there's the quarry. 900 meters from the temple, up a gentle slope, lies the source of these giants. Here, partially released from the bedrock, sit 3 more enormous blocks that never made it to the temple. The most famous is called Hajar el-Hibla, the stone of the pregnant woman. This monolith measures 21 meters long, 4.8 meters wide, and 4.2 meters tall. Its weight is estimated at 1,000 tons. In the 1,990 seconds, archaeologists discovered a second massive stone in the quarry, partially buried beneath the stone of the pregnant woman. Then, in 2014, the German Archaeological Institute uncovered a third monolith, even larger than the others. This forgotten stone measures 19.6 meters long, 6 meters wide, and 5.5 meters high. Current estimates place its weight at approximately 1,650 tons, making it the largest worked stone block ever discovered from antiquity. These abandoned giants tell us something crucial. The builders weren't just lucky. They were deliberately cutting stones of extraordinary size. The quarry stones show clear evidence of ancient tooling, wedge holes, trimming marks, and the systematic approach of experienced stoneworkers. Someone planned to move these massive blocks. They'd already moved 3 equally large stones successfully. They knew what they were doing. The question that has haunted archaeologists, engineers, and historians for centuries is simple: how? Before we can answer that question, we need to understand what we're really asking. Moving a 800-ton stone isn't like moving a large boulder. It's a precisely orchestrated engineering operation requiring knowledge of friction, load distribution, mechanical advantage, material strength, and logistics. You need to know how to cut the stone without cracking it, how to separate it from the bedrock, how to transport it without sinking into the ground, how to elevate it, and how to position it with precision. Modern engineering would approach this problem with massive cranes. The largest mobile crane in the world can lift about 3 tons, but only under ideal conditions, with carefully prepared ground and the object positioned directly beneath the crane. Even this behemoth couldn't easily handle an 800-ton stone block with the dimensions and weight distribution of the Trilithon stones. In 2012, when the Los Angeles County Museum of Art needed to transport a 340-ton boulder from Riverside County to Los Angeles, a distance of 105 miles, it required a custom-built 206-wheeled transporter and 3 powerful trucks working in tandem. The move took 11 nights and required extensive route planning through 22 cities. Engineers hailed it as one of the largest megalith movements since ancient times. The Trilithon stones weigh more than twice as much, and they had to be raised 7 meters into the air and positioned with perfect precision, 2,000 years ago. So when someone says the Romans couldn't have moved those stones, they're partially right. We don't fully understand exactly how they did it, but the evidence is undeniable. Someone did move them. The stones are there. They're real, they're precisely cut and positioned. And they've been sitting in that wall for roughly 2,000 years. The question isn't whether ancient engineers could move 800-ton stones. They demonstrably did. The question is, how did they figure it out? To understand how the Trilithon was moved, we need to break the problem into stages: quarrying, transport, elevation, and positioning. Each stage presents unique challenges that would test the limits of ancient engineering. The limestone quarry at Baalbek shows clear evidence of systematic extraction. Ancient stoneworkers used a technique called plug and feather, or wedge and groove. First, they'd cut a series of holes along the line where they wanted the stone to separate from the bedrock. These holes were typically drilled or chiseled about 10 to 15 centimeters deep and spaced at regular intervals. Into each hole, workers inserted 2 thin metal pieces called feathers and a wedge between them. By driving the wedges progressively deeper, moving from hole to hole in sequence, they could create even pressure along the entire cut line. As the wedges were driven in, the stone would eventually crack along the predetermined line. This method allowed for relatively straight, clean cuts, even in massive blocks. The abandoned stones in the quarry show evidence of this technique. They also reveal another crucial detail: the stones were cut on 5 sides while still attached to the bedrock. Only the bottom remained connected. This meant that once freed, the stone would essentially be resting on a prepared surface, ready to be moved. Bronze and iron tools of the Roman period were more than capable of working limestone, which is a relatively soft stone compared to granite or basalt. The Trilithon stones are made of local limestone with a hardness of about 3 on the Mohs scale, comparable to a copper coin. Iron chisels and bronze saws with abrasive sand could cut this material, given enough time and labor. Moving an 800-ton stone 900 meters across slightly sloping terrain is where ancient engineers had to truly innovate. Several pieces of evidence in experimental archaeology give us clues about how this might have been accomplished. The key principle: you must reduce friction while distributing weight. Roman engineers were masters of the pulley, the lever, and the capstan, a vertical winch turned by multiple workers walking in a circle. The Roman architect Vitruvius, writing in the 1st century BCE, describes complex lifting machines using multiple pulley systems that could multiply human force by factors of 10 or more. For horizontal transport, the Romans almost certainly used a combination of wooden rollers and sledges. Experiments by modern archaeologists have shown that wetting the ground in front of a sledge reduces friction, dramatically cutting the force needed to move a heavy object by up to 50%. This technique was definitely used by the Egyptians. Tomb reliefs show a man pouring liquid in front of sledges, carrying massive stones. But here's where the engineering gets sophisticated. You can't just put an 800-ton stone on wooden rollers and push. The pressure would crush the rollers instantly. The stone would sink into the ground. You need to distribute the load. Archaeological evidence from the quarry suggests the Romans built a wooden framework around and beneath the stone, essentially a massive cradle. This cradle would spread the stone's weight over a larger surface area. The cradle itself would then rest on multiple rollers, each bearing only a fraction of the total weight. A German research team in the 1,990 seconds calculated that moving the Trilithon stones would have required approximately 16 capstans working in coordination. With 32 men operating each capstan, 512 workers in total per stone. The capstans would be anchored ahead of the stone with ropes running through pulley systems attached to the cradle. As the workers turned the capstans, the stone would slowly inch forward. Rollers behind the stone would be retrieved and repositioned in front as it advanced. The process would be painstakingly slow, perhaps 10 to 20 meters per day at most. But with 900 meters to travel, it would take 45 to 90 days of continuous work to move a single stone from quarry to temple. Multiply that by 3, and you're looking at nearly a year just for transport, not including preparation time. This explains something puzzling about the abandoned quarry stones. They likely weren't abandoned because they were too heavy to move. After all, the builders had already moved 3 similar stones successfully. More likely, they were abandoned for practical reasons, perhaps structural flaws were discovered, or perhaps the building project was halted before these final stones could be transported. Some scholars suggest they were left unfinished when the Roman building program ended in the 3rd century CE. Raising an 800-ton stone 7 meters into the air presents a different set of challenges. The Romans couldn't build a crane strong enough to lift this weight. No wooden structure could support such a load concentrated at a single point. Instead, archaeological evidence suggests they used a ramp system combined with lever mechanisms. The principle is simple. If you can't lift something straight up, raise it incrementally. Here's the likely process. Once a Trilithon stone reached the building site, workers would begin constructing an earthen ramp leading up to where the stone needed to be positioned. As the ramp rose, the stone would be pulled up the incline using the same capstan and pulley systems used for horizontal transport. The genius is in the ramp's design. By making it long enough, you reduce the slope, which reduces the force needed to pull the load upward. A ramp 7 meters high but 50 meters long has a gentle 14% grade steep, but manageable with enough mechanical advantage. At the same time, the foundation stones beneath where the Trilithon would rest were already in place. The stone would be pulled up the ramp until it was level with its final position, then carefully maneuvered sideways onto the foundation using a combination of levers and wooden fulcrums. Rock physicist Jean-Pierre Adam conducted detailed calculations in the 1,970 seconds, showing this method was feasible with Roman-era technology. The time required, approximately 6 months per stone for the complete elevation process, including ramp construction. The final challenge, positioning an 800-ton stone with millimeter precision. This is where ancient engineering truly shines. The builders likely used the technique still employed in some traditional construction today. The stone would be set slightly above its final position on wooden rollers or bearings. Workers would then remove material from beneath the stone incrementally, allowing it to slowly settle into place. By carefully controlling which supports were removed and in what order, they could walk the stone into its exact position. The tight joints between the Trilithon stones weren't achieved by cutting them perfectly. They were achieved through a final trimming process after the stones were in place. Masons would mark areas where stones touched unevenly, remove the stone, trim the high spots, and reposition it. This iterative process, repeated multiple times, created the precision fits we see today. Evidence for this technique comes from masons' marks found on some of the stones and from the stones themselves, which show signs of in-place trimming on their edges. The entire process, from quarrying to final positioning, probably took 2 to 3 years per Trilithon stone. With multiple teams working in parallel, the complete Trilithon could have been constructed in perhaps 5 to 7 years. For comparison, medieval cathedrals often took 50 to 100 years to complete. The scale is different, but the principle is the same. With enough skilled labor, enough time, and enough determination, humans can move mountains. Or at least 800-ton pieces of them. To truly appreciate Baalbek's engineering achievement, we need to understand the historical context. The Temple of Jupiter wasn't built in isolation. It was part of a broader tradition of monumental construction spanning millennia. The Romans were brilliant engineers, but they didn't invent large-scale stone construction. They inherited and improved upon techniques developed over thousands of years across the Mediterranean and Near East. The Egyptians had been moving multi-ton stones since the Old Kingdom. The granite blocks in the King's Chamber of the Great Pyramid weigh about 50 tons each, and were transported over 800 kilometers from Aswan to Giza, then raised nearly 50 meters into the air. The largest stones moved by the Egyptians, the Colossi of Memnon, weigh over 700 tons each, and were transported 700 kilometers overland. The Greeks mastered precision stone fitting and developed sophisticated lifting devices including the crane, the pulley system, and the Lewis bolt, an ingenious wedge device that grips stone from inside a carved hole, allowing it to be lifted without visible external attachments. These Greek innovations were eagerly adopted and refined by Roman engineers. By the time the Romans began construction at Baalbek, they had centuries of experience with large-scale building projects. Roman engineers had constructed the Colosseum with its 80 vertical shafts and complex systems of ramps and pulleys for raising exotic animals from underground chambers. They had built the Pantheon, whose 43-meter dome remained the world's largest unreinforced concrete dome for nearly 2,000 years. They had engineered aqueducts that transported water hundreds of kilometers across varied terrain. The Temple of Jupiter at Baalbek was built during the reign of Augustus and his immediate successors, a period of unprecedented Roman wealth and ambition. The empire controlled the entire Mediterranean basin. Resources flowed to Rome and to prestige projects throughout the provinces. Baalbek, strategically located on trade routes to Damascus and the east, was designated as a colonia, a settlement of Roman citizens with special status. The temple complex wasn't just religious, it was political. Its massive scale broadcast Roman power to locals and to traders passing through from Persia, Arabia, and beyond. The message: Rome has the wealth, the skill, and the determination to move mountains. Literally. But here's something fascinating. The Trilithon stones may not be entirely Roman. Their architectural style differs from the typical Roman construction visible in the upper parts of the temple. They show greater weathering. They use different stone-fitting techniques. Some archaeologists believe the Trilithon may incorporate foundations from an earlier Phoenician or Hellenistic structure that the Romans built upon. If true, this wouldn't diminish the achievement, it would expand it. It would mean the tradition of moving massive stones at Baalbek spans not just centuries, but millennia. The Romans, encountering an already impressive foundation, decided to match or exceed it with their own massive construction above. This pattern of building upon earlier sacred sites was common in the ancient world. Jerusalem's Temple Mount shows similar evidence of construction from multiple periods. The massive foundation stones, some weighing over 600 tons, were laid during Herod's expansion of the Second Temple, but they incorporated and built upon earlier Israelite and possibly Canaanite structures. The practical reason for using such large stones becomes clearer in this context: prestige and permanence. Smaller stones would have been easier to work with, certainly, but massive blocks made a statement. They said, "This structure will last forever." This place is sacred beyond measure. The effort expended here reflects the importance of what happens within these walls. There's another, more technical reason. In seismically active regions like Lebanon, massive foundation stones provide superior earthquake resistance. Their weight makes them incredibly stable. Their size means they can shift slightly during earthquakes without the structure above failing. They act as a kind of shock absorber. Smaller blocks might separate during seismic activity, compromising the entire structure. The Trilithon, despite Lebanon's earthquake history, has remained stable for 2 millennia. This suggests the builders of Baalbek weren't just showing off, they were solving a genuine engineering problem. How do you create foundations stable enough to support a massive temple in an earthquake zone? Answer: use stones so large that the earth itself can't easily disturb them. The Trilithon represents something profound about human civilization, our willingness to invest enormous effort in projects that outlast any individual lifetime. No single person who worked on the Baalbek Temple lived to see it completed. Workers who quarried stones in their youth became elders who supervised younger workers doing the same. Generations of families labored on this project. Modern construction projects are typically planned in terms of years, perhaps decades at most. Ancient builders thought in terms of centuries. The cathedral builders of medieval Europe had the same mindset. They knew they were building for their grandchildren's grandchildren. This long-term thinking enabled achievements that seem impossible when measured against a single human lifespan. You don't need to move an 800-ton stone quickly, you just need to move it surely. You don't need to finish the temple this year, you need to ensure your children can continue the work. The Trilithon embodies this philosophy. Each stone required years to quarry, transport, and position. But the builders had time, they had patience, they had a vision that extended beyond their own lives. And so they built something that would still stand, still impress, still inspire awe, 2,000 years after the last worker laid down his tools. Despite more than a century of archaeological investigation, Baalbek still holds genuine mysteries. Not mysteries that require aliens or lost civilizations to explain, but puzzles that remind us how much we still don't know about ancient engineering capabilities. One of the most perplexing aspects of Baalbek is the near-complete absence of contemporary Roman records about its construction. The Romans were meticulous record keepers. We have detailed accounts of numerous Roman building projects, including cost breakdowns, labor requirements, and construction techniques. Yet for Baalbek, one of their most impressive temples, we have almost nothing. No inscription names the architects, no ancient historian describes the construction process, no cost records survive. This silence is unusual and has fueled speculation. Some researchers suggest records may have been lost in the chaos of late antiquity, when Baalbek was conquered by various powers and eventually damaged by earthquakes. Others point out that quarry operations and construction sites weren't typically recorded in detail, only the finished monuments received inscriptions. The most likely explanation is prosaic. The records existed, but weren't copied during the medieval period when most ancient texts were preserved. Thousands of Roman documents were lost simply because no medieval scribe thought them important enough to copy. The technical details of moving large stones probably seemed less interesting to medieval monks than philosophical or religious texts. Still, the absence of records means we're reconstructing ancient methods through indirect evidence. Tool marks on stones, analysis of structural techniques, comparison with other sites, and experimental archaeology. It's like trying to understand how a watch works by examining the finished product without ever seeing the watchmaker at work. Why were the 3 massive quarry stones left unfinished? This question has multiple possible answers, and the truth might involve a combination of factors. The simplest explanation: the building project was halted. Roman construction at Baalbek continued intermittently from around 15 BCE to the 3rd century CE. Political instability, economic downturns, or changing priorities could have ended the work at any point. The quarry stones may have been destined for an expansion or renovation that never happened. Another possibility: structural concerns. Close examination of the stone of the pregnant woman reveals a crack. Perhaps this crack or similar flaws in the other quarry stones made them unsuitable for the temple. Ancient builders would have been acutely aware that a cracked stone could catastrophically fail if raised 7 meters in the air. A third theory: the stones were intentionally left as a demonstration of skill. Ancient quarries sometimes left their largest blocks in situ as advertisements of the quarry's capabilities. "Look what we can cut," they seem to say. "If you want stones this size, we can provide them." Some researchers have proposed that leaving large stones in quarries was a religious practice, a kind of offering to the gods of the earth, thanking them for yielding their stone. While speculative, this idea gains support from evidence at other ancient quarries where finished or nearly finished objects were deliberately left behind. The discovery of the third, even larger stone beneath the others in 2014 adds another layer of mystery. Was this stone cut even earlier, or was it cut later, after the first two were abandoned? The stratigraphy and relative positions are still being analyzed. Perhaps the most intriguing mystery involves the possible pre-Roman origins of some of Baalbek's massive stonework. As mentioned earlier, the Trilithon shows architectural features that differ from typical Roman construction. The stones are larger than Romans typically used, the jointing technique is different, the degree of weathering suggests they may be older than the Roman temple above them. Some archaeologists have proposed that the Trilithon represents an earlier, possibly Phoenician or Hellenistic foundation that the Romans incorporated into their temple. This would make sense. Sacred sites were often continuously rebuilt on the same location across centuries. Each new culture would add to or modify what came before. Bronze Age remains have been found beneath the temple, dating back to the 3rd millennium BCE. The site was clearly important long before the Romans arrived. Could some of the massive stonework predate Rome by centuries, or even millennia? Here's where careful scholarship becomes crucial. Some alternative historians have claimed the Trilithon is far older than mainstream archaeology, admits perhaps 10,000 years old or more. These claims typically rest on either misinterpreting archaeological evidence or cherry-picking data while ignoring contradicting evidence. The balanced view. Some elements of Baalbek's foundation may indeed predate the Roman period, but probably not by millennia. Phoenician construction at the site is well documented. The Phoenicians, like their Canaanite ancestors, were capable stoneworkers and builders. They could have created impressive foundations that the Romans later built upon. This would explain the architectural anomalies without requiring unknown ancient civilizations. Ongoing archaeological work may resolve this question. Modern dating techniques, including optically stimulated luminescence and analysis of tool marks, can provide more precise dates for when stones were cut and worked. Excavations beneath the temple continue to reveal earlier occupation layers. One fascinating question, rarely asked: how did knowledge of moving massive stones spread across the ancient world? The Egyptians moved multi-hundred-ton stones. The builders at Stonehenge transported stones hundreds of kilometers. The Inca fitted massive blocks with impossible precision. Baalbek moved its Trilithon. Similar achievements appear in places as far-flung as Easter Island and Angkor Wat. Were these independent inventions, or was there knowledge transfer? We know the Romans studied Greek engineering. We know the Greeks had contact with Egypt. We know trade routes connected the Mediterranean with the Near East, Central Asia, and even India. Did engineers travel? Did they write technical manuals that haven't survived? Was there an ancient equivalent of academic conferences where builders shared techniques? Or did each culture independently arrive at similar solutions to the universal problem of moving massive weights? The archaeological evidence suggests both. Some direct transfer of knowledge through conquest and trade, and some independent innovation. The Lewis bolt, for instance, spread from Greece throughout the Roman Empire. But some techniques, like the water lubrication method for reducing friction, were probably invented multiple times in different places. These mysteries don't diminish Baalbek's achievement, they highlight the sophistication of ancient engineering networks. The builders at Baalbek drew on a deep well of accumulated knowledge, experimented with new approaches, and pushed the boundaries of what was thought possible. And that's exactly what great engineers always do, in every age. The stones of Baalbek teach us lessons that extend far beyond ancient engineering. They speak to fundamental questions about human capability, technological progress, and what defines advanced civilization. One of the most persistent myths about ancient construction is that it required advanced technology in the modern sense, power tools, computers, sophisticated materials. The Trilithon demonstrates otherwise. The builders used bronze and iron tools, wooden machines, rope, human and animal power, and most importantly, knowledge. Knowledge isn't primitive. Understanding leverage, friction, load distribution, and material strength represents sophisticated engineering even if implemented with simple tools. A modern engineer with a calculator might work faster than an ancient engineer with an abacus, but both are applying the same fundamental principles of physics. This distinction matters because we often equate technological sophistication with tool complexity. But some of humanity's most impressive achievements came from brilliant application of simple principles. The Roman arch required no advanced materials, just a deep understanding of how stones under compression distribute force. The dome of the Pantheon was built with increasingly lighter concrete toward the top, reducing weight without sacrificing strength, a principle rediscovered and refined in modern skyscraper design. Ancient engineers were constrained by their tools, but not by their intelligence or creativity. They solved problems we struggle with today precisely because they couldn't brute force solutions with powerful machines. They had to think deeply about mechanics, plan carefully, and execute flawlessly. Modern construction operates on compressed timelines. Projects are measured in months or years. Delays cost money. Speed is valued above almost everything else. Ancient construction operated on different assumptions. The Temple of Jupiter took roughly 200 years to complete across multiple generations. Workers expected to dedicate their entire careers to a single project. The concept of finishing quickly barely existed. This patient approach enabled achievements difficult to replicate today. When you have years to move a single stone, you can use slow but reliable methods. You can train workers to extraordinary skill levels. You can refine techniques through iteration. Modern attempts to replicate ancient construction sometimes fail not because we lack technology, but because we lack time. Experimental archaeology projects typically have funding for weeks or months. Ancient builders had decades. That changes everything. There's a profound lesson here about the relationship between time and quality. The rush of modern life produces impressive things, but rarely does it produce things built to last millennia. Ancient builders created structures meant to outlive empires. That requires thinking on a timescale we've largely abandoned. Another common misconception: ancient engineers couldn't have planned complex projects without modern mathematics. While Romans did have mathematics, it was relatively basic by today's standards. They used Roman numerals, which make complex calculations difficult. They had no algebra, no calculus, no computer modeling, yet they built the Colosseum, the Pantheon, the Aqueduct of Segovia, and the Temple of Jupiter at Baalbek. How? Through empirical methods, scale models, and accumulated experience. If you don't know the mathematical formula for an arch, you build a small arch, see if it stands, then build progressively larger ones, refining your approach with each iteration. After a few generations, you've developed rules of thumb that work reliably, even without understanding the underlying mathematics. This empirical approach has advantages. It's robust to theoretical errors. If something doesn't work in practice, you see it immediately and adjust. Modern engineering, relying heavily on computer models, sometimes produces designs that work in theory but fail in practice because the models omit some crucial variable. Ancient builders had no choice but to test their ideas at full scale. This made their knowledge hard-won but extremely reliable. When a Roman engineer said a structure would stand, he based that claim on actual experience with similar structures. His confidence came not from calculations, but from observation. This reminds us that mathematics is a tool for understanding, not understanding itself. The principles of engineering exist, whether or not we can express them mathematically. Ancient builders understood these principles through direct experience and careful observation. Why use 800-ton stones at all? This practical question touches on something deeper: the purpose of monumental architecture. The straightforward answer: prestige, religious devotion, political power. Massive stones impressed people then as now. They demonstrated the power of whoever commanded the labor and resources to move them. They created a sense of permanence and stability. In a world where most buildings were made of mud, brick, or wood, a stone temple declared, "This will stand forever." But there's more. Monumental projects serve social functions beyond their stated purpose. They organize labor, created economic activity, trained skilled workers, and fostered civic identity. The workers who spent years moving the Trilithon were part of something larger than themselves. They could point to those stones and say, "I helped place that." Their children and grandchildren would see those stones and remember. In this sense, the difficulty of moving 800-ton stones wasn't a bug, it was a feature. The very impossibility of the task made completing it meaningful. If the stones had been easy to move, moving them would have carried less cultural weight. Modern society builds quickly and efficiently, but we've lost something in the process. Few people spend their entire careers on a single project. Few projects are designed to last centuries. The connection between builder and building has weakened. Ancient monumental architecture created intergenerational connections. Great-grandfathers who quarried stones, grandfathers who transported them, fathers who positioned them, and sons who carved decorations all worked on the same structure. The building became a family legacy, a thread connecting the living to their ancestors and descendants. The Temple of Jupiter stands in ruins today, damaged by earthquakes, weathered by time, and partially dismantled for building materials in later centuries. Yet, the Trilithon remains. Those three massive stones, placed with such effort 2 millennia ago, still rest in their foundation, still fitted tightly together, still inspiring awe. They've survived the rise and fall of empires. They've outlasted the Roman Empire, the Byzantine Empire, various Islamic dynasties, the Crusades, the Ottoman Empire, and the French Mandate. They've witnessed history while remaining unchanging, a stone monument to human capability. In 1984, UNESCO designated Baalbek a World Heritage Site, recognizing its universal value to humanity. Today, despite political instability in the region, archaeologists continue to study the site. Each excavation season reveals new details about construction techniques and the site's complex history. The Temple of Jupiter at Baalbek reminds us what humans can achieve when we combine knowledge, determination, and patience. It demonstrates that advanced doesn't always mean high tech. Sometimes it means brilliant application of fundamental principles. It shows that our ancestors weren't primitive or less capable than us. They were simply working with different constraints and different timelines. Most importantly, it proves that some achievements transcend their original purpose. The Romans built a temple to Jupiter, but what they really created was a testament to human ingenuity that would inspire people from entirely different cultures, speaking different languages, worshiping different gods, for thousands of years after the last Roman worker laid down his tools. That's the true legacy of Baalbek, not the stones themselves, but what they represent, the boundless capability of human minds to solve seemingly impossible problems. We began with a mystery. How did ancient builders move 800-ton stones with what we often dismiss as primitive technology? We've explored the evidence, the theories, and the archaeological research. We've seen that while we don't know every detail of the process, we understand the broad strokes, and what we understand is impressive. But here's what I find most remarkable. The mystery isn't that ancient people did things we can't do today. With modern cranes and hydraulic equipment, we could absolutely move 800-ton stones. We've moved larger weights. The mystery is that ancient engineers figured out how to do it without any of our advantages. No computer models to test structural loads. No steel cables capable of bearing enormous weight. No diesel engines providing immense power. Just human muscle, animal strength, wooden machines, and brilliant engineering intuition built up over generations of trial and error. That's the real wonder of Baalbek. Not that the Trilithon exists, but that human beings, limited by the technology of their time, refused to accept those limitations as defining what was possible. They looked at 800-ton stones and said, "We can move these." And then they figured out how. This mindset, the refusal to accept impossible, drives every great engineering achievement. The ancient builders at Baalbek had more in common with the engineers who landed humans on the moon than we might think. Both faced problems that seemed insurmountable. Both invented new techniques when existing ones weren't sufficient. Both succeeded through a combination of brilliant planning, meticulous execution, and sheer determination. So what do you think? Does understanding how the Trilithon was likely moved make it more impressive or less? Does explaining ancient engineering diminish the wonder, or does it transfer that wonder from the mysterious to the demonstrable? Drop your thoughts in the comments. Tell me, what other ancient engineering marvels would you like to explore? The precision-fitted stones of Machu Picchu, the acoustic properties of ancient amphitheaters, the Antikythera mechanism, the 2,000-year-old astronomical calculator? If you enjoyed this deep dive into real history and real engineering, hit that like button and subscribe. And remember, the past wasn't inhabited by aliens or lost super civilizations. It was inhabited by humans. Humans just as intelligent as us, just as creative as us, just as capable of solving impossible problems as we are. They moved mountains. We can too.